Hello? Yes. Hi. So my name is William. I am a developer with Microsoft, coming all the way from the United States here today. So yeah, thank you for having me. Uh, so yeah, I'm a developer that's been working on the SDV project at Microsoft. I'm here with Filipe. If he wants to say anything, I think.
Yeah, so good morning, everyone. So I'm Filipe. I think, not a newcomer to this community, right? It has been almost like 1 year that I had the pleasure to be here for the first time that Microsoft showed our first contributions to the Eclipse SDV. We also planned to have Jordan, which is another software developer that is working from our team on this companion to Eclipse Ibeji, and I hope that you like what we are going to show and contribute.
Yeah, so as it says up here, we'll be talking about Freya, which is a companion to Eclipse Ibeji and to other digital twins, and so it's an update to that project here. Yes. So before we get into some of the technical details, we can have a little bit of fun, talk about the name. So this project takes its name from the Old Norse goddess Freya. And so those of you that are familiar with Ibeji may know that we picked this name because Ibeji is the name of a spirit in the Yoruba religion that represents some twins. And so we had a similar idea here. We chose Freya because she is a twin. Her brother's name is Freyr. And she's associated with this concept in Norse mythology called Seidr, which is magic for seeing and influencing the future. We also have a few other fun facts in here. She's also associated with fertility and gold, rules over a heavenly field called Folkvanger. She's a necklace called Brisingamen, a cloak of falcon feathers, a boar named Hildisvini, and rides a chariot pulled by two cats, which is my favorite part up here. So now we'll talk about why we're making this project and a little bit into what it actually does. So the software-defined vehicle, of course, needs to connect to the cloud for data synchronization, command processing, analytics. You know, all sorts of things need to happen in the cloud. It's not just on the device. But this is a hard problem if you have different vehicles that have different in-vehicle digital twin models. Maybe they have different ECUs on different models and so on. And so you want to try to synchronize that on some common model in the cloud so that you can write your analytics just based on a single model rather than who knows how many. And so this new capability aims to solve that problem. It creates a flexible framework for that synchronization between the instance digital twin, which is what we're calling the vehicle state, and then the digital twin in the cloud, which we're also calling the canonical digital twin. So we have a simple architecture diagram here. I'm not going to talk too much about this now because we have a video where we'll go over it in detail. But the main thing that I want to point out while we're here is that we have a number of different interfaces here with this. Is there a pointer on here? Okay, well, yeah, there we go. So we have this interface here with this mapping service. Again, we will talk about this later. We have an interface here with the cloud, and we also have an interface with the vehicle digital twin and everything that happens on the vehicle. So all of this will be customizable. You can, you simply just need to write your own definition for an interface. And so we're designing this from the beginning with extensibility in mind. And here, this just talks a little bit about those interfaces and what they do, and then some details about the traits and so on. So again, we'll cover this in the video coming up here. We also, if you're coming back to this, we have a little animation. Do you want to do this, Filipe?
It's just, so we have all of this covered in the demo, and we really want to show you the code. We were planning to do a walk through this animation, but in the end, the code just talks by itself. This is kept for you. Of course, the slides are shared, and then we can take questions offline. This is just an explanation on how we consider that having two different vehicles with two different digital twins, with two different, I would say, property names or signal names, if you want, or even data model or data properties. The solution that we are proposing to the community is to help and be able to synchronize the cloud's digital twin which is a canonical model of your vehicle, into different instance models that you have between multiple vehicles, and that's basically this companion. You will see us talk about this later on. You will see the demo using a digital twin from Microsoft on the cloud side. We did that just for the demo, and that you are going to see on the code. The code is completely cloud agnostic, and you can use it, for example, with any implementation of a digital twin that you want to run on AWS or GCP or even whatever digital twin that you have, okay? Sorry? Dito is also an option, right? This is completely accessible. The code is already out there. It's pushed into it's one of the repos inside Ibeji. It has no dependency on Ibeji, neither on Chariot, so you can use it just as a standalone. But again, for the sake of the end-to-end demo, we just decided to do this demonstration, okay? So let's go.
So I think next is the demo itself. Yeah. Is it?
My name is William, and I'm a developer working on the software-defined vehicle project at Microsoft. Today, I will be covering the new Cloud Sync component, also known as Freya, which will be an update to the Eclipse Ibeji project. I will start by going over the architecture, and then I will show a demo of the new features live in action. So first off, what is Freya? Why are we doing this? So Freya is designed to facilitate data synchronization between the vehicle and the cloud. But this is a potentially difficult problem because vehicles might all have different schemas for their data. They might have different signal names. They might have different things that they support and so on. But in the cloud, you might want a single model, so-called canonical model, or maybe a small set of those models so that it's easy to reason against them. So Freya intends to help solve that problem. In the diagram here, we see Freya has two components. The first is called the cartographer. This piece will communicate with an external mapping service. And this can live in the cloud, as we see in this sample diagram. It can also live on the device or as some sort of hybrid. Freya is flexible and allows you to implement the mapping service and any of the other connections to however your needs dictate. So the cartographer will talk to the mapping service. It will get information about which signals it needs to collect data about, as well as how often the data needs to be collected, and some instructions on how to translate that data from vehicle-specific model to a cloud-specific model. The cartographer will then send that data over to the emitter component. The emitter component will communicate with Chariot to discover the vehicle digital twin service, also known as Ibeji. This part is currently not implemented, so you will not see Chariot in the demo later, but it is planned for the future, and so it's part of this diagram. Then once the emitter knows how to talk to Ibeji, it will query Ibeji for the providers that are necessary to meet the requests from the mapping service. And then from there, it will communicate with the providers, acting as a consumer to collect data from them. Then, according to the schedule from the mapping, the emitter will emit the data. It will first go through a cloud connector, which again can be customized to your individual needs. And then from there sent up to the cloud, where the data can be collected and reasoned against and so on. So now that we've covered the architecture, let's get into a demo. So this demo will be using Azure Digital Twins as a sample implementation, but Freya has no specific ties to Azure. You can implement your own connector to connect to any other cloud solution that you want. We're just using this as a demo here today. So here we're looking at the Azure Digital Twins Explorer, where we see we have two instances of vehicle here called V1 and V2. These are created using the models that we see on the left. So we can look at these very quickly. We have a vehicle which has two relationships with an HVAC and an OBD. That HVAC contains an ambient air temperature signal, which is in Celsius, and then a Boolean indicating whether the air conditioning is active. We won't actually be synchronizing this property today, but it's part of the model on the vehicle, so we've tried to mirror it in the cloud. And then our onboard diagnostics right now has one value, which is the hybrid battery remaining, which is expressed as a percentage. So now we're going to go to the vehicle itself. So we see four windows here. The top two will be representing one vehicle, and we'll start with one first. And then the bottom two will be for the second vehicle, where we'll replicate everything, but with some different configuration and different signal values to illustrate how the mapping service works. So I will start by running the in-vehicle digital twin service on the first vehicle. So this is also known as Ibeji. And then we will run the mixed provider that Ibeji has. This simulates an ECU and handles all of the signals that we saw on the cloud side. So in vehicle one, everything is configured to be identical to the cloud. So all of the IDs are the same name, all of the units and everything else about these signals is exactly the same. So the only translation that needs to happen is packaging it into an Azure format. Then we will also start the mixed consumer. So this will just read the data from the provider and act sort of like the dog mode demo, where if the temperature gets too high, it will turn on the air conditioning and bring the temperature back down. So we can actually see that now it's turned the air conditioning on. The temperature is decreasing. It was 31 degrees. We're now at 28 degrees, and this is also depleting the battery. So in this other window, we will run the cloud connector component. This particular one is written in .NET, and it connects directly to Azure Digital Twins. We're working on a more complete sample, which first talks to Event Grid via MQTT and then is routed to Azure Digital Twins. But this one just goes straight from the device directly to Digital Twins. And then lastly, we will start Freya. So this is using a mapping service which is internal to the Freya application. There's nothing external running. It just helps keep the configuration easier to use and more contained, and I don't need as many windows. So we see here, when it starts up, we see the cartographer detects mapping work, meaning that there's something new that it needs to start mapping. And then it takes a little bit for it to pick up the data. So we see here, we're starting proxies, which will receive the data from the Ibeji provider over on the left. And then here we have our first time that we're emitting data. So we're emitting, in this case, the ambient air temperature, and the value is 30 degrees. And shortly afterwards, we're also here emitting the battery percentage. So we can scroll down here, and now we can look at the cloud side. So that one is configured for vehicle one. And if we look at vehicle one, we see here some data. Right now it's 31 degrees Celsius in the car, and the battery percentage is 86%. And it's pretty warm, so we should see this number start falling. There it is, 29. And of course, the battery will fall as well. It was 86, now it's 84. So now I'm going to start up a second vehicle, which has a different configuration, and we will see this configuration. So I'm running all of the same services, they're just configured differently. So we start with Ibeji. Now we do the provider. And then, of course, the consumer. And so what differs here is both the signal names and the units for the temperature. So in vehicle 1, we see we have a signal called hybrid battery remaining, but in vehicle 2, this is simply named battery percent. And similarly, vehicle 1 has a signal called ambient air temperature, whereas vehicle 2 has one called interior temperature. We also see that the temperature here is in Fahrenheit. So 72 Celsius would be crazy. This is in Fahrenheit. So now we will start up the other cloud connector as well as the other instance of Freya. And then we'll see data synchronized to the other vehicle in the cloud, which is using the same model, but the data is coming from a different a vehicle with an instance that is configured differently. And we will also see the unit conversion. So let's give it a minute. The first emission of data can take some time. So we see here instance ID is vehicle 2 HVAC as opposed to vehicle 1 in the other side. So it's done, it's emitted the data. We should be able to see it pretty soon here. So in vehicle 2, there it is. You'll notice that instead of being in the 70s degrees Fahrenheit, it's converted the value to Celsius for us. And the hybrid battery is there as well. And we see that even though vehicle 2 has been configured differently with its providers, it's still synchronizing with the same model in the cloud. And that is, of course, thanks to the mapping service. So that concludes this demo. Thank you for watching.
Yeah. There's a few key takeaways that we want to highlight here. The first is that Eclipse Ibeji aims to provide the capability to express that digital representation of a vehicle through an extensible, open, and dynamic architecture, so that you can access the hardware and your sensors and so on. So, you know, in the demo we saw Azure, but there's nothing stopping you from writing a connector for any other cloud solution. And then the Ibeji's architecture has that in-vehicle digital twin service as its core, and that captures all the vehicle's primary capabilities and makes them available to the Ibeji consumers. And the providers expose a subset of the primary capabilities by registering them with the in-vehicle digital twin service. So that's just a quick review of Ibeji. And then Freya aims to solve that hard problem of digital twin synchronization, providing, again, a flexible framework for that synchronization between the instance digital twin on the vehicle and the canonical digital twin in the cloud. And again, just reinforcing that flexibility. We demonstrated this with Ibeji, but you could also customize that part of the solution and use Freya with any other in-vehicle digital twin that you want. And your DTDL properties, so you saw some sample versions that we came up with at Microsoft just to do the demos, but they can be based on any other syntax that you want, such as Covessa VSS or whatever else you might have in mind. And then we also have support for multiple communication protocols. So like on our roadmap right now, we're working with General Motors to have an Eclipse U protocol implementation in Azure. And then, of course, a connector for that you can use with Freya as well. And so here we have, this is everyone that's working on SDV at Microsoft. So not only me and Jordan and Filipe, but everyone else. So we've got a good team of good people all working on all these pieces to get them working together. So yeah, that's it. Thank you for having me here, for letting me talk. Maybe we have some questions. No questions?
So we just heard about data spaces, right?
Mm.
So data spaces needs a feeder from a digital twin inside the vehicle, right? So is this already interfaced, or are you planning to?
Yeah.
Yes.
We are of course looking at that. I was also quite happy to see the presentation from ZF because I think it will be amazing. For example, or express in DTDL your digital twin implementation, and even, for example, why not taking some of the connectivity? Again, as we wanted to highlight, this is not really related to Azure at all. It's completely cloud agnostic. We also, William mentioned, we are looking at integrating more protocols, so that is really protocol agnostic for communications. We did not use an MQTT broker for cloud connectivity, but we could use some of them that exist, for example, like Canto that has been presented today. And basically what we are moving forward in terms of next steps is really build blueprints with as much projects as we can within the Eclipse community so that we can have a complete software stack for in-vehicle and cloud.
And to say a little bit more about that, the cloud connector you saw here was connecting directly from the vehicle to Azure Digital Twins, but we are working on one now that instead uses MQTT, so our sample will again be using Azure, of course, but this MQTT broker could communicate to whatever you want up in the cloud.
Yeah, so there's a question.
Thank you. Peter from AVL. I was wondering, is this translation based on basically on name matching, or is there some semantics behind as well?
So at the moment, it is based on name matching. We haven't explored a lot of some of the more semantical ways to do this just because the problem is a little bit harder, and we've only been working on this for 5-6 months now. But that would be down to how you configure or implement a mapping service. So we've sort of separated all that out so that you can customize that, do something a little bit more advanced if you want to than whatever samples we're providing here.
Thanks.
Yeah, so one more quick question. So it sounds like Freya is really independent from the digital twin, from everything else. Did you think about making one new project, and why did you think about adding it as a spin-off?
Yeah, we did.
Yeah,
we did. We wanted to release this as soon as possible to the community so that we can get as much collaboration as possible. And the fastest way, as you know, is really actually to have a repo under the existing projects. As we mentioned, it's completely independent of Ibeji, it's independent of Chariot. And so if the community thinks that there is value, we will do the necessary effort and groundwork to create a new project. We submit it, and again, we just continue from there. Okay. Yeah.
Thank you.